Okay, I appreciate you all being here. And I'm here today with two of my students, Min An and Min Tuan, as well as my associate, Ahmed, over there. So unfortunately, we are not as entertaining as Huizing and Gao Wei. We are actually from the university, so I have to be, my default way of speaking is a little bit more formal, okay? So just like Huizing was saying that she can go from the whole spectrum of Singlish to King's English, I can also go from the whole spectrum of Singlish to King's English, except that my default is here. But I know I'm not speaking King's English, but my default is closer on this side rather than on the Singlish side. But just like Huizing asked you to trust her that she can speak King's English, I ask you to trust me that I can speak Singlish, except that I'm not speaking Singlish right now. So I apologize for that. Okay, so for the next 45 minutes, my three colleagues here will be sharing with you a project which Min An and Min Tuan devised and conceptualized. And I think briefly, I think I'll just hand over to you and then you take over. Okay, so we'll switch it. Since you are the ones who authored the slides, you do it. Yeah. You do it, and then we will. Okay, so without further ado, I'm just here to let you know that we are from the National Institute of Education, and this is an independent research project authored by my two students from St. Joseph's Institution, who are next year going to Hwa Chong Institution. Okay? Yep. Okay. Thank you.
Right, so good morning, everyone. My name is Tuan, it's Min An, and today we are going to share with you our Life2Well project, without frying your brain. So, as you may have known before, microclimate is the climate of a very small restricted area. So, for example, those of us sitting right here in this hall right now is considered a very small microclimate compared to that outside of the street, which can be hotter and different in some aspects. And it affects humans in their physiological well-being. For example, their mood, their concentration, and thermal comfort, which is suggested by Liu and company in 2019. And according also by him, climate change has reduced human thermal comfort and health. Microclimate can also impair our body thermal regulation with serious consequences, and it can lead to many health diseases or damages to our body in the long term. And microclimate also has an impact on the functioning of the brain. And like, for example, you may have been very annoyed by your noisy neighbors who always make a lot of noise at night. Right, so the rise of technology has made EEG research more accessible to the mass, and that is one of the aspects that we're focusing on in our project. And we use it to identify human stress level, as according to a research paper by Holt and company in 2015. And furthermore, EEG can be an indicator of physical health, strongly related to the change in human physiological health, like for example, in heart rate variability and in heart rate. And EEG at the same time can be sensibly used to investigate human productivity. And in our project, we use the 10-20 EEG placement system as seen on the figure right to your right. And we selected channel FP1, FP2, and so on, as you can see in the diagram as well. And these channels have been used in past research to detect fatigue and attentiveness.
Okay, so next I will talk a bit about our Life2Well system. So Life2Well is our attempt to connect the bridge between our mental and physical well-being, as indicated by our heart rate, our physical response data, which mean the biometric data, as well as the mental data, which is the brain wave, which is measured by the EEG headset or electroencephalogram headset that we ourselves made. And next is to measure the environment, we use devices that we make on our own. as you can see, is this unit over here, a very small unit that we make with microprocessor as well as some very common sensor to measure the environment around the participant. These devices can be worn on the waist of the participant and to measure various very common factors such as the noise level, light intensity, temperature, humidity, pressure, carbon dioxide concentration, and dust concentration. And one more thing I want to show you is the headset that we make to measure the EEG data. So you can, Tuan, can you open it and maybe show our headset? Yes. Okay, so this headset is to be worn on participants in sessions when they were to do their homework or maybe work in different jobs, mostly while they're sitting or doing a specific task that require cognitive abilities. So just this headset alone can measure the brainwave from different regions of the brain. Then we validate this headset against research-grade equipment to ensure that our data is accurate. And then we use the data from our headset in our regression model. And as you can see, this headset is made mostly of tape, which is why we managed to reduce the price of the EEG headset to as low as possible. From devices that only accessible in research lab to something that we as students can buy and use. So yeah, this is, as we tell ourselves, is a very important step in citizen science, where we make equipment that once unobtainable for laymen like us to be able, for us now to be able to use in very casual settings. Next is, okay, next slide please. Okay, so this is just the wiring diagram and all the sensor data or the microcontroller that we use for our devices, for our this module, in environmental module. So this one is just like some info. We also incorporate data from the Singapore weather station to incorporate more data points to our data set. Now next is, okay, so this is some information about how we process our data. So the way we process the data is quite well, it's quite structured. So firstly, we have to process data through Python with standard libraries. Then we use libraries such as NumPy, Pandas, sklearn, and we detect outlier with different algorithm like z-score method to remove unwanted data points. And we draw correlations, we train random forest regression model or CN model for EEG data. And then we, now next one is Chevy summary plots, which we use to interpret our results from our regression model. So maybe, so as you may know, that the regression model that we train is usually interpreted as a sort of a black box, which is basically we don't know what happened inside them. So we attempt to decipher the black box with Shipley summary plots. And lastly, we also use deep learning to train EEG data. So so now is all our talking. So we will move straight to the activities, which will help you to go through our process of Life2Well and how we make the process from scratch. So maybe Mr. Ahmed, you want to continue with the activities.
Hi everyone. So we're gonna present you with 3 activities, which are intended to give you a little bit of hands-on to have a better sense of what our process was in creating this project. Let me shift this over to presentation view. There we go. All right. So as we mentioned before, this project involves data collection from 3 sources. One is data about your local microclimate. The other is biometric data, which we collected using smartwatches. And the third is the EEG data. Just now you saw the headset. So in order to collect microclimate data, we actually designed our own custom, An and Tuan designed their own custom sensor. Let me go through a little bit more about what exactly is involved in this. What you're seeing in my hand is sort of the final product, something which is nice and compact and wearable. If you can see in my hand, it's actually got clips so that you can attach it to your belt. That was the way they did the design, so it will be comfortable to wear with their school uniforms in particular. Let me go through what's inside. So we've got a microcontroller. We use ESP8266, specifically Node MCU. We have a CO2 temperature and humidity sensor. We have a PM2.5 sensor to detect the dust level. We have barometric pressure sensor, sound sensor, and then we have a hub to help us with all the wiring, and an external power source. Oh, you might have noticed that there's a USB cable dangling from this unit. That's because the power source is not inside the box itself. You have to connect it to like a power bank, which can be in your bag or like in your pocket or anything like that. So what we'd like to spend a few minutes doing right now is to do, let me go through some of the design considerations first. So you can see here, this is a top-down view of how the sensors and electronics components are arranged. There's a couple of important factors. First important factor is heat management. We have to make sure that, for example, the temperature sensor isn't being heated by the microcontroller or by another component, so that the temperature we are sensing is representative of the outside temperature, not of the temperature inside the box itself. Another consideration is that while most of the sensors need to be exposed to the outside environment, maybe I should take this off. Yeah, because otherwise you're just recording whatever variables are in the box. So you need holes for the different sensors. At the same time, this is a wearable device, so it needs to be somewhat resistant to physical damage. It should be, yeah, should not be so sensitive that if you knock into it, all the connections come loose. And it's Singapore, it rains a lot, so it needs to be, you need to find some way to weatherproof it, basically. And of course, it has to be fairly small so that you can actually wear it. So we'd like to go through a bit of a design exercise, an interactive one. I think everyone here has at least their own phones as devices. We also have some papers and pencils and some materials. So you can decide whether you want to sketch out your own design on paper, in which case you can get some papers from us, or you can scan this QR code. There's like a Google Jam board which you can use to just sketch online. So the idea here, you can think about things like, if you were going to design a wearable sensor, where would you want to wear it? Like if you don't want to put it on your belt, where would be another good location? Would you want to wear it on your arm? Would you want to connect it to a hat if you wear hats? So it's pretty open, and the nice thing about this kind of DIY design is that we like the fact that people can change the design based on their own needs, basically. So let's try this out. Yeah, you've got the link there. And if anyone wants materials, just come up to us. We can pass you whatever you're interested in using. So let's spend about, until 11:30 on this, and then we'll switch over to the next activity. So it's currently 11:25. So we'll take about 5 minutes on this.
Probably for this design, you may want to consider maybe sometimes maybe the position on the participant waist is not the best one to put it. Maybe you can put it as a sort of a smartwatch, maybe, or as a maybe a hat. Can be also acceptable as well. Um, and another consideration maybe you want to consider is where to design the prototype so that the components take the least space as possible. So as this is sort of a wearable devices, we want it to be as small as possible to not basically create any discomfort for the user, as well as to maybe any. So yeah, so for the waterproof, there must be a sort of a layer that cover the all the sensor face, right? So how to make a layer that sort of is not too thick that is will affect the recording, but thick enough to make the device maybe a bit resistant to impact or to rain. Tuan, do you have any advice?
I think one way you can do it is actually make, for example, if you want to expose a light sensor to measure light intensity, for example, you might just want to place a thin layer of tape or clear materials over it, such that in a way it doesn't really affect the light intensity that is shown upon the sensor. And in some cases where, actually in some cases where the sensors are not in contact with the environment, for example, you can actually have greater insulation against the environment so that it can protect the sensor. Yeah, so basically those are some of the recommendations and some modifications we think that it can suit your need in creating your own wearables.
Okay, so
So yeah, just taking a look at the whiteboard, I think there's different frames, so people might be designing on others. You didn't have to remove, but whoever did the design just now, I think someone was conceptualizing something which looked more like a watch. I can share something. There are different designs of sensors available online, but the components we use are, it's one of the limiting factors lah. So what I'm holding up right now is one of the bigger components. It's actually the CO2 sensor. You can see it's a black block with a blue backing. There are other CO2 sensors available online with different sizes, but roughly you'll run into sizes like this. The dust sensor is also similar in size. Thankfully, the microcontroller is fairly small. This isn't the exact model of ESP8266 that we used, but they're all around the same size. And yeah, they all need to be crammed together. It would be possible to do something which is on your wrist, but it will be quite a bit bigger than a watch lah. All right. Let's move. Oh, we have a question. Yeah. That's a very good question. So basically, if I understand correctly, your question is, do we need to have all the sensors in our own unit, or can we use some of the readings from which are collected from public data sources around Singapore? Do you want to? Okay. Yeah.
the thing is, the reason why we specifically use the word microclimate because it's a very specific climatic condition around the user, right? So it changes rapidly from one place to another. For example, if you're in an air conditioned room, and of course that's this place can be much colder than outside, which is below the hot sun. And carbon dioxide concentration is, of course, no exception. Maybe in an air-conditioned room, you would expect the carbon dioxide concentration to be a bit higher due to the aircon. Or if you're in maybe a jungle, perhaps, then maybe the concentration is not too much high, or when you're near a construction, the carbon dioxide concentration may be much higher than normal. This change in carbon dioxide concentration may affect our mental and physical health, as we will show you in the last activity. Yes, thank you.
So we'll move on to the next activity now. So yeah,
Okay.
I'll hand over.
Okay, so the next activity is to interpret EEG results. So as you know, we measure our EEG results with our headset, but to make this recording meaningful, we need to be able to interpret it, or we need to be able to get some useful information from it. So of course, this is just a very simple simulation of our process. Of course, we will have to continue from these results to basically to figure out how the microclimate condition affect our EEG data. So this one is just very simple. So this one helps us to determine whether or not the microclimate factors actually affect our mental state. So we want to determine whether or not there is any correlation at all from the environment to our EEG data. So we'll start from next slide. Okay. So there's actually 9 main periods in our data, each period with differing environmental factors. For example, there will be a period where the door is closed, so maybe it's a bit more suffocating, or there will be a period where the light is off, for example, which make it darker, and for some of the participants, they may feel discomfort from the fact that they have to work a specific task in a dark room. And for some of the period, there is the aircon is on, for some is off. So there's a change in temperature. So these changing environmental factors may lead to the fact that the participant may feel comfort or discomfort mentally and physically. And we want to determine whether or not the discomfort from the changing environmental factors impact the EEG measure from our data. Now, first we have to have maybe a feel of how the participant feel when there's changing environmental factors using self-reported mental and physical state. So as you can see on the score over here, which is rated from 1 to 10, the participant feel most comfortable in period 1 and periods 7, 8, and 9. And they feel most discomfort in period 4, 5, and 6. And maybe next. Okay, so our EEG data that we collected will be then processed into different features, non-linear features, which is basically so sort of common features that you may know is, of course, the mean, the average, maximum, and minimum. So those are very common features. Now we want to extract features that are usually used for these type of measurement or these type of tests, which are the trended filtration analysis, approximate and sample entropy, and then we perform ANOVA tests on those features to compare between the period. So now I would like to explain what the ANOVA test mean. Maybe next slide. Okay, so an ANOVA test is basically to measure whether or not the range of the features between the two periods are similar or not, which means that to determine whether or not the EEG signal between the two periods are similar or not similar. So for example, you can see that, so to determine whether or not it's similar or not, we based on p-values, which is basically values that have a maximum of 1, means that the range of features are the same. So for example, when we compare 1 to 1 is of course 1, which means that the EEG data in period 1 is the same as the EEG data in period 1 because it's the same data set. So if the value is high, for example, 1 and 7, this is high, which means that the EEG data are very similar, which means that the participant may feel very similar between the periods. So it's either discomfort or concentration or attentiveness is very similar for the two periods, which means that, so if there is any effect between the environmental factors to our mental state, then there will be a correlation between the periods that has the same environmental factors, as well as the same p-value. So high p-value when compared 1 to 7. So low p-values, of course, means the reverse, which means that the two periods are very different. So this means that there's a drastic change in our EEG signal between the two periods. For example, when it's 0, for example, 1 and 5 for this one, which means that period 1 and period 5 has no similar EEG sort of signal, which means that the participant feel very different when compare period 1 and period 5. So next slide, please. So this is our, so as you can see, this is our procedure here. And for example, for period 1, we got the light is on, and period 2, there's the lights on and door is open, but the aircon is off. So based on this one, we can see that there's changing environmental factors throughout period 1 and 9. So if there is an influence of the environment to our mental state, there should be a correlation between this and our EEG signal to see if there's any, to see if the changing in the period leads to any similar p-values, high p-values when comparing the two similar period with the environmental signal. So with all this information, what can be interpreted from the table, from a given table, as well as what you think is the most comfortable period for the participants based on these signal, based on these table, as well as what environmental factors that impact the participants' comfort level the most. So maybe I will give you maybe 1 or 2 minutes to look through all the table to see if you can interpret anything from the tables, and what maybe and answer some of this question as well.
The top left section is actually showing you the experimental setup. So the periods from 1 to 9, each represents a period of 5 minutes. And the participants were doing a set of tasks, the same task throughout the whole time, basically. It's just that we change the environmental conditions every 5 minutes. So for example, period 1, is it the door is closed? Yeah, period 1, door is closed, light is on. Period 2, door is open. Period 3, the light is off, and then so on. But yeah, you can see the changes listed. And for the self-reported data, in terms of the numbers, basically, high is good. High means they feel better, basically, for the self-reported mental state and physical state.
Okay, so any of you have any interpretation or anything yet you want to tell us about what can you say from these, what can you conclude from these tables? Any of you have any idea or any conclusion that you made up about the table? Okay, so maybe I would just give you one clue. Maybe pay attention to the one that's sort of more red than others. So, which means that they are similar, right? Maybe we can just check where if the period 1 and period 7 are similar. So we have to check that with the table over in here. Maybe our setup. We see that period 1 and period 7, although they don't have, they are different in terms of like aircon and door opening or closing, but they are very similar in the fact that both of them have the light on. And this is, and it's interesting to see that when the light's on, it seems that period 1 and period 7, 8, and 9 are very similar, because as you can see in the data over here, 1 is very similar to 7, 8, 9. 7 is very similar to 8 and 9, which means that there are very high similarity between 1, 7, 8, and 9. So as you can see here, it's correlated with the fact that all of these 1, 7, 8, and 9 all have the lights on, which means that the participant feel very comfortable and are very concentrated on a task when the lights on. And it shows in our both in our self-report data as well as the result of our EEG data, which means that there is a correlation between the participant, how the participant feel with the environmental factors. Any of you have any conclusion, any other conclusion that you can make up? Okay, yes. Yes? Yes. Yes, they are working like very simple geographical task, which is basically to calculate the mean of the data and determining what is the best location to grow like different type of food, example. And so yes, they will have to repeat the same task 1 time or 2 times to determine whether or not there is any changes, just based on the environment factors, because the task will be the same throughout. Yes. Yes, having the lights off seems to not only decrease their comfort in the self-reported data, but as you can see in the ANOVA results as well, 4, 5, and 6 actually have very high correlation, which means that yes, when the lights off, there is certain discomfort that the participant feel, and it's also confirmed to us, particularly that our model does mean something. There's certain correlation between the environment factors. In this time, is the lights. And to our EEG data, which means that we can proceed with the data processing as well as interpretation and regression model, etc. So yes, so this is our second activities, and this is basically just the start of how we deal with our EEG data. So next, I will invite Tuan to host the third activities.
Right, so ultimately, our goal in this project is to find out the effect of the microclimate on our well-being, both in our physical health and our mental health. So after collecting and comparing of the preliminary data that in the step that Anne has mentioned before, we now use those data and train a machine learning model. And after training the machine learning model, we use the Shapley summary plot to interpret the results. So as you can see on your right, here's a Shapley summary plot. In this case, is a model for our heart rate. So in Shapley summary plot, the variables are ranked in descending order of importance. So this is the feature importance. For example, as you can see on the left of the diagram, we have the CO2 underscore, the sound underscore, CO2, and so on. And based on the order, we can say that the concentration, carbon dioxide concentration is more important than sound, more significant than sound in affecting our heart rate. So and furthermore, right, we do some simple exponential smoothing on the models. So each environmental feature had its smooth counterpart, which you may wonder why we have CO2 underscore and CO2 and sound underscore, dust underscore, as well as the normal variable without the underscore. So it's derived from the values of the feature from the preceding hours, with all the values being exponentially less important than the current value. So for example, for the feature ft, right, we have ft minus 1, which is directly before it. ft minus 2 is directly before ft minus 1, affecting the current ft, but ft minus 1 will be more important to ft than ft minus 2, ft minus 3, and so on. And you may be wondering what are the numbers 2021, 17, 19, 16 means. So the features, the numbers from 0 to 23 represent the hours of the date that the data points were taken, while number 31 to 37 represents the day of the week from Monday to Sunday. And these features are binaries, so 1 or high means that it is true, or 0 or low means false. So for example, if a data point was recorded at 6 a.m. on a Monday, then 6 and 31 would be 1, and the remaining binary features would be 0. And finally, the color, as you can see from the scale right here, a blue color would mean the low, a low value of the observation, and the red color or the dark pink color would mean a high value of that observation. And in this way, right, Shapley summary plots combine the feature importance with the feature effects, which is how the variables such as carbon dioxide concentration, sound, dust, and so on affects our heart rate, and as well as the magnitude, which how it affects. Okay, so from this, what can you interpret from the figure? Having all of the points with different colors and the Shapley value, and as well as the different feature importance. So maybe I will give you, please have 1 or 2 minutes to think about this. Okay, so maybe I'll just answer that question as well. So as you can see, the middle line right in the middle is the normal or the average value of that feature. So for example, for carbon dioxide concentration is 580 parts per million. Towards the right of the axis, it will be a value greater than 580 parts per million, and towards the left of the vertical axis will be less than 580 parts per million. And similarly, we have calculated other values for sound and dust and temperature as well. So as you can see, in order of descending importance, heart rate is affected the most by carbon dioxide concentration, followed by ambient sound, then ambient temperature, dust concentration, and air pressure. So for the magnitude of how these feature affects our heart rate, carbon dioxide concentration, if it is lower than 580 parts per million, as you can see by to the left side of the middle vertical axis, it can either lower or higher heart rate. It can lead to lower or higher heart rate. For ambient sound, if it's higher than 10, which is our calculated value, it is higher. It leads to higher heart rate. And in terms of other factors, inhaled dust, or otherwise PM2.5, it increases stress response, and in turn the inflammation of lungs and narrowing airways, and finally it increases the heart rate, which is similar to what we have found out in the Shapley summary plot as well. And this is research done by Breacher in 1999, which is congruent to our findings. And one more interesting aspect to point out as well is that heart rate usually decreases at night, and that is when we sleep. Right. Thank you for listening. This is the end of our presentation. If you want to find out more about our work and our progress, then here's the QR code and our link to Dr. Lim's website. Right. Thank you so much.
Okay, so another round of applause for Dan.